During steady state heat conduction, the energy content of the wall is going to remain constant because there is no accumulation of energy. During transient heat conduction, there may be some accumulation, and therefore the energy of content of the wall may not necessarily remain constant. The drink placed on the table without the blanket will warm up faster, as a greater degree of heat transfer will occur to the air rather than the blanket, because there is an increase in resistance R from the increase in insulation. For a glass window over which heat transfer is occurring, we can find the Q dot and the inner temperature at that inner wall by analyzing it with resistance. So we can see that from T infinity 1 on the inside, the resistance of convection to the inner surface, to the resistance of conduction to the outer surface, through the resistance to convection on the outer surface to the ambient temperature. So we can add up those resistances because they are in series, and then we can calculate Q dot, and then from Q dot we can calculate delta T because we know delta T over that inner surface is equal to Q times R. So Q times the resistance of convection at the inner surface is going to be equivalent to that delta T, so we find that there. Here we're finding a Q representative for this complex situation that in terms of resistances involves an inner temperature over a resistance of convection to an inner surface to sheetrock resistance, and then we have two parallel resistances of wood studs and fiberglass, another level of sheetrock, an outer temperature convection, and then a ambient temperature. We know those resistances in parallel are equivalent to this, so then we can, that is in series with the other ones in series. We add up all these resistances for our different forms for convection and conduction, and then we can calculate the total resistance and find the representative Q from that using our relationship for Q, the T infinity 1 minus T infinity 2 over total R. And then to find the total Q, we multiply the Q representative by the area over the representative area. For this, I chose 12 meters by 0.65 meters. Here we have a pipe where we want to find the T surface temperature, and we're going to have to iterate T for this. We make some simplifications initially, assuming that it's a gray body and a black body, and the T surrounding is equal to T infinity. To simplify this, H of radiation down so that we can use H naught for the H of radiation and the H of convection on the outside surface. So here we see we've got from T infinity 1 inside over convective radiation to the inner surface, conduction to the outer surface, and then convection and radiation, which are parallel, but here we're using R naught based on our simplifications to the surrounding temperature. We put that all together with an initial guess for T, and then we can iterate until our calculated T from delta T equals QR from the inner surface to the outer surface in order to find a suitable T. Here mine was unreasonable, I'm not sure why, but my method is correct. Finally, we do some dimensional analysis with known techniques including heat capacity in order to find the velocity of the water in the pipe. Comparing equivalent terms for steady 1D heat conduction and mass diffusion, we have Q dot to M dot, K to the diffusion coefficient, dt dx to the D concentration dx. Higher density wall is not going to increase the rate of mass transfer. Doubling the thickness of the wall is not going to double the mass transfer. Higher the temperature will increase the rate of mass transfer, and other things being equal, doubling the mass fraction will not double the rate of mass transfer. Finally, mass diffusion through a wall with some known dimensions allows us to find this mass diffusion per area for two different given lengths.